in the lab, no eating in the lab, no running around. The floor should always be dry. When passing over the sharp instrument, you'd pass the handle first, though that is much of woodwork. When you are putting glasswares on the working benches, you make sure that you don't put them closer to the bench, closer to the edge. Yeah. So those are very important in order to safeguard the children during the lab session. B. Oh, it's already there. State one important of chemistry in our day-to-day life. Why do you think chemistry is important?
It helps. It helps in preparation of different medications.
It helps
In preparation of medications.
in preparation of medicines. Now, when you say importance of chemistry, chemistry is very important in many ways. One of the ways could be in our homes. The other one could be in hospitals. The other one could be in the construction. The other one could also be in agriculture, right? But the statement here is saying in our day-to-day life. So they have actually specified. So you can say anything in those lines, in the industry, in the construction industry, in the agriculture, in our homes, in breweries, many others. So it helps in preparation of medicine. It's one, but we can also provide another one. It in our homes, it helps in the manufacturing of detergent. Because had it not been for chemistry, it would be very difficult for us to make detergents. So that's because the question is open-ended, it has not specified any way in which our question should actually be. Yeah. Any question from there?
No, I'm clear.
Hello, sir.
Hi, Miambo.
Sorry, I took time to join.
It's okay. You just apologize to Messi. Messi is my old friend. She requested to join. She's from my old school. So Messi is a very good person. You are very safe. She doesn't insult. She doesn't treat people. A very good person.
All right, sir.
So Messi, meet Miambo, one of also my good friend from my current school.
Hi.
Hello.
How are you?
Fine, thank you. And how are you?
I'm good.
Yeah. So I promise you, I will attend to your needs differently. Yeah. You should be able to submit the areas of uncertainty. Sometimes we might have same common grounds. This one saying I didn't understand this. This one says I didn't understand this. So we might throw a lesson for everyone to benefit. And sometimes if the lesson is extracted from what you know, it may be taken as a revision, right? Yeah. So Miambo, we just started looking at this paper. I'll send you a recording so that we don't have a repetition of what was presented. We are actually now on question 1B.
1B. Then I haven't missed that much.
No, we just started that. So 1B says the following graph shows heating curves that were drawn after pure ice and candle wax were heated over time to their melting points. So they've told us categorically, they have told us that pure ice, it's a solid, right?
Yes.
Candle wax is also a solid until they melted. So these three things are actually pointing to the fact that what we are dealing with is a heating of a substance until the melting actually happens. Miyambo, can you comment on X? What would you say about X? What do you see about the graph? And Messi will have something to say about Y. Miyambo, over to you.
Okay, give me a sec, sir.
Messi, if you are ready, you can hold the floor.
So I'm still thinking.
No.
For X, isn't that not melting taking place?
Yeah, it's a melting taking place, but the form of melting is actually different, and that's what I want you guys to comment on.
What do you mean the form of melting, sir?
I don't know if you guys are not seeing. For me, what I'm seeing is that the lines for X are not straight, are a little bit zigzag.
Yes, I've noticed that.
That's the point I wanted you guys to say.
Sir. Okay.
No, we are trying to compare the two, right? So our comments should be based on the differences that we are seeing.
All right.
Yeah.
I get it.
Messi, do you agree that your line is straight? Your lines are straight?
No.
Oh, sorry, Messi doesn't agree. Can you look at the lines for substance Y?
Mm-hmm.
Have you seen that the lines are straight? Let me show you what I actually mean. What I actually mean is that from here, we have a straight line going all the way up to that. And from here, we also have another line going all the way up to that. They are straight. We don't only have a single curve at that point where actually the melting is taking place.
Mm-hmm.
While for Y, there is no, if I'm to put up that line, you can see that there's some gaps being left in between because these lines are not straight.
Yes.
As a result, we are able to tell which one is for wax, we're able to tell and which one is for pure ice. So what would we say? Which one is for pure ice?
Why?
Okay. And which one is for pure X? Which one is for wax?
X.
X.
So may I know the reasons why you've settled for that?
Because of the way the graph was going, so.
You can't put up that as a reason to send to ECZ for marking because of the way the graphs. You have to give more information.
I'd say because candle wax takes more time than pure ice to melt. That's my thinking, sir.
But before we even ask for other opinions, if I'm the one marking your paper, I would say no to that right from the beginning. Because when you say higher than the other, we don't have values there for us to defend our reasoning.
Okay.
Yeah. So one thing that we need to know for sure is that kendo is a mixture, right?
Yes.
So what we know about mixtures is that their melting points are not definite. And that is the reason as to why you have actually seen that the line for X is not definite. It's quite zigzag. While for Y, which is for pure ice as a pure substance, one of the properties that they have is that they have a definite melting point.
So what causes it to not have a definite melting point, sir?
It is because there are a lot of impurities. So those impurities are the ones that will actually affect the way the melting does. I'll give you an example. When you are alone running, you're going to have a smooth running, right? Because you don't have anyone disturbing you.
Yes.
But now if I say Messi and Miambo, I'll tie both your left leg and the other one a right leg, the way they do when they are racing, maybe below the ankle somewhere there. And then I say run. You will not have a perfect running because one is dragging the other one. Exactly. So the presence of the impurity causes the fluctuation in the way the melting will actually happen.
Okay. Thank you, sir.
So
Understood.
you're welcome. So our answer, as we say, the candle wax is for cave. Cave what? Now remember, when you are now, these are examination techniques. They have already started writing for you here. They have already started writing for you cave. So all you just need to put is X or Y. Don't repeat. They have already indicated for you. So candle
So
wax.
if they didn't put that, that's when you can see.
Exactly.
Okay.
So the reason is because it does not have a fixed melting point. It does not have a fixed melting point. As simple as that.
Okay.
Messi, are you okay?
Yes, sir.
Okay. Good. So we can now move on and go to the other question. So that was all for question. No, not part of it, of course. So now 2, which is a continuation, says, give one effect of impurities on the melting point and boiling point of a pure substance. What do you say?
Doesn't it make the process longer than usual because of the impurities contained?
Okay.
Yeah.
Now, remember, I was telling you, I don't know if it's you or the other students I was telling, that when you are answering questions, let there be a very good write-up to a point whoever reads will, of course, understand. What happened? Okay. To a point, whoever reads will be able to understand that the one who wrote is a student. What do I mean? When you say it takes longer, that statement is very, very underrated. Do you know why?
Okay. No, sir.
When you say it takes longer, it could be that the amount of heat is less, and the other one says it takes less time. It could be that the other one, the amount of heat is more. Miss, are you hearing from that? So meaning the answer that you give has to give a wedge boundary that all other factors are included. So the best that you do talk about is in terms of temperature. Maybe one has got a higher melting point, the other one has a lower melting point. Meaning even if the heat, the amount of heat supplied on both is different, but we are looking for the degree, the temperature at which the melting or the boiling actually happens. Yeah. So the melting and boiling increases when impurities are added. And for your own information, the same thing I'm giving you today is the same thing I was teaching about Form 1 yesterday. They guys, the grade 8s are actually learning these things.
For real, sir.
Exactly.
The curriculum has changed there. It's become serious.
So now, how do you prove this point? Messi, have you ever cooked beans before?
No.
No. Miambo, have you ever seen someone cooking beans?
Yes, I have.
So if you are cooking beans, especially in the pot, not a pressure cooker, beans
Yes.
in there are acting as impurities. Beans, salt, tomato. In our village, we even add sugar. They're acting as impurities.
Sir.
They're acting as impurities. So when
Yeah.
you have an electric kettle containing heated water at 100 degrees, because this water may be perceived to be pure, it will boil at 100 degrees Celsius. But the soup which is in these beans what you are cooking, the temperature is actually above 100 because of the presence of impurities. How do you test that, or how do you prove that? When you get this water and pour in here, beans stops boiling. For some reason it stops. Why? Because the amount of heat because the water that you have introduced in this pot is containing lower temperature, which suggests that the temperature at which this beans is boiling is higher than 100.
No. Okay.
Yeah. We can actually, there's a very, for Messi, those students that I taught years back, I did this experiment because there's a principle which talks about melting and the boiling points, elevation, and the freezing point are decreasing. That's what actually happens. So when we add impurities, the melting and the boiling point increases. Should I say they increase these points, and then the freezing point decreases? How do you prove that the boiling point, the freezing point decreases? When you have pure water, you put water in a sachet,
Yes.
and you have another water. Within this water, you add a lot of things such as maybe stone, just sand. When this thing becomes very strong and you allow them to melt, you realize that this one will melt faster. Because the melting point is lower, but the one that contains impurities will take longer to melt.
Okay.
Yeah. There's even another documentary on the internet where in the World War years when those soldiers were fighting, they were actually making bridges using ice. But now that ice they were using, they were just adding impurities to make it a little bit harder. Exactly. I can look for that documentation, then I can share with you guys watch on your own. But there's that documentation which is still emerging from the fact that when there are impurities, the pure substance becomes stronger, its melting point increases, and its freezing point decreases, and once it freezes, it becomes very strong.
Just because of impurities.
Because of impurities, exactly.
Okay.
Yeah. Okay, so that was the end of question 1. It is a very important question that you can answer. Fine.
Okay.
B is talking about separation techniques. Yeah. So now for B, it's actually talking about separation techniques. And separation techniques is also very important. I was actually, for you, Miambo, I was just talking to Mr. Ndlovu. And for you, Messi, I might share this concept with Mr. Silung where we still communicate, where sometimes we need to organize scientific trips.
Okay.
Talking about separation techniques, we can go to Lusaka and Water Storage Company. They do a lot of separation during, like the thing I was teaching you, Miambo, about water purification. We can write to
Yes, sir.
Lusaka Water and Storage Company. We go to Kafue. Kafue is near, so that we go and learn.
Yeah. That's not the issue, sir.
So sometimes when we learn things from outside the environment, especially explained by people who work in those industries or whatever places they may be, it adds a bit of importance to what we actually just learn in class. So I was talking to Mr. Ndlovu, and I'll write an email to Mr. Maziopa so that maybe we can make follow up on that.
All right, sir.
So from what we have here, we have two liquids, liquid P and liquid Q. Accidentally, what did we do? We
You
mixed.
mix them.
And when we mixed them, we discovered that there was no layer of separation between P and Q. They mixed uniformly. So if I was to ask Miambo, which one, so mention one liquid, then Messi also mentions another liquid, but we need to work as a team.
Any liquid.
Any liquid, but don't give us a hard one so that Messi has difficulties to find the matching liquid. No. It's very bad, I know. One.
Water.
Exactly. So we'll have water. Messi, what substance do you think, what liquid do you think we can add to water so that when we mix them, they don't show any layer of separation?
So I'm not sure. I won't even lie.
You are very sure, Messi. There are other liquids that you can add to water and they mix uniformly. Do you agree?
Yes, I know.
Or
Methylated spirit.
exactly.
Those two are mixed uniformly.
Water and methylated spirit. Yes. Actually,
I'll see it when I believe it, sir.
please, there's something that is contained in ethanol. There's something that is contained in methylated spirit. They are both alcohols.
Oh.
Yeah. That's why.
Oh, yeah. Okay, now I get.
That's why in Bunsen burners we can use methylated spirit. We can still use ethanol. They burn the same thing.
Which one is safer when you're doing a project? Methylated spirit or ethanol?
It depends on the concentration. Both of them are very bad. Messi understands. They left a scar on my hand.
What was the scar, sir?
Yeah, it's methylated spirit.
Oh.
Yeah. So these two are perfect examples of liquids, which when we mix them, they do not show a layer of separation. Now the question is, what name is given to such liquids? Which when we mix them, they don't show any layer of separation. What name is given to them?
Miscible liquids.
Exactly. So ethanol and water are a perfect combination for mixtures that are called miscible liquids. Mercy, do you take note of that?
Yes, sir.
Good. B says, what is a separation technique that we can use and what criterion is used to separate these mixtures? So sometimes I might ask, who is your best friend? This one says, May says, no, my best friend is Kaluva Mtambo. I don't know if he's still there. Miambo says, no, my best friend is Yolonimo. Then the question is, what criteria are you using to choose those ones as friends?
What do you mean by criteria, sir?
As in, what property do we follow? So the criterion could be the difference in melting point, or maybe the solubility, or maybe any other criteria that we can actually look at that these contents have, which are different, that when we are to separate them, our method of separation depends on those differences. I'll give you an example of maybe you and Yolonimo, and then I ask to say, in which way can I separate these two? I would say, Yolonimo doesn't love the rains, and you enjoy the water. What will I do? I'll just pour water on both of you. The one that doesn't like the rains will run away. It's a perfect separation.
Okay.
Yeah, that's the way I can explain a criterion. So
Okay.
to start with, what method of separation can we use?
Fractional distillation, I think.
We have gone a bit far.
Yeah.
Can you use a simple one?
Hello? So,
Hi. Sorry, I received a call on my phone. So because I'm using the same network, and you know how these guys, the Apple guys behave. The phone comes to the phone, a call comes to the phone, it's able to ring on the laptop. That's what disturbed. My apology.
it's okay, sir.
Yeah. So the simple distillation is the best because these are just two. They are just two, so we don't need to go as far as fractional. Fractional usually happens for miscible liquids that have very close boiling points, of course. So now I've already answered the question. The criterion that we are using is the difference in what? In the boiling.
Point.
That's our criteria. Why? Because water boils at 100, right?
Yes.
And if we use the ethanol boils at what? 78. So this in itself is a better criteria because we're just going to hit them. The one with a lower boiling point, what happens? It evaporates and it is collected first before the other one actually starts boiling. So that's another way in which you can separate them. Yeah.
Okay.
Exactly. And for C, we have already answered them. We're just giving them the names. We're deducing them. So we already have one, which is water. Here, there is no particularity which one should be water. They are just identities that we are giving them, actually.
So in this question in general, you're just supposed to put your N liquids.
Any liquids, but provided they should have a different boiling points as our criteria, and those two, when mixed, they should mix completely without showing any form of layer in terms of separation. Are we okay?
Yes.
Okay, sir.
Yeah. You can write that.
Okay.
Done.
Good. We have 5 minutes remaining before we go to the second and last session. Miambo, are you done?
Yes, I'm done, sir.
I'll still upload this video recorded on my YouTube channel, and then I'll gladly share with you so that you can replay and learn from those that missed.
Oh, you're streaming live.
No. I am offline, but I'm recording the presentation.
Oh, okay.
Which Lena will have to Much later. Apple has got a lot of restrictions. It's difficult to. I don't remember having just learned how to streamline the how to go live on YouTube while using Zoom. Yeah. So
No.
B3 says the following symbols show a nuclide of element A. When you talk about nuclide, we are actually talking about the symbol which we have, it's A, and remember, doesn't represent an element. You don't have any element on the periodic table that has got A. Then we have the mass number. We also have the atomic number. So the question
Okay.
is, distinguish between the number 16 and the number 32 in the nuclide. What do they stand for? What do they mean? That's what they mean by saying distinguish. What would we say?
16 is the atomic mass, and then 32 is the proton number.
Yeah, you are very right. 16 is the atomic number, while 32 is the mass number.
Okay.
16 is the number of protons, while 32 is the number of protons and the neutrons, which we can call the mass number. Yeah, that was very good.
Of neutrons.
Now the question is, to which group of the periodic table do they belong?
Which one, sir?
The same, does this element belong? Sorry, this very element, to which group of the periodic table does it belong?
Group 6.
Yeah, group 6.
So you write the configuration, which is 2,8, making it 10, and then the last remaining is 6. But these groups are written in Roman numerals. So it's 5, then 6. That's very good.
Okay.
That's very good. So the question now is, if we know where to find it, then we're going to use the periodic table to identify it. What name is given to this element?
It's sulfur.
Yeah, exactly. This element is actually sulfur, which is just way, way above oxygen. Yeah, that's very good. You guys are doing good. Once we do a lot of revisions, believe you me, you start crying for XZ to send you exams to write so that you don't forget.
Mm-hmm.
Okay, and now the last one, because we don't have a minute. Draw a dot and cross diagram to show the bond formed in a compound between an element A and hydrogen. So, because this is just above oxygen, the same way oxygen and hydrogen react to form water is the same way this element will actually react with the hydrogen to form water. They have not told us to include all the elements or the electrons. So if you want, you can just say A. We put these electrons 1, 2, 3. These are crosses. 4, 5, 6. And then we draw 2 atoms of hydrogen on both sides. Hydrogen here and hydrogen here. We indicate them as H here. We indicate them as H here. And then we use dots to represent electrons coming from hydrogen.
Okay.
Is it making sense?
Yes.
Yeah. So that's what actually happens.